Hello students. Today, I am going to start our lecture that we started on thermodynamics in the previous classes. So, in the last class, we have talked about the different kinds of enthalpies. So, if I go back to our previous lecture, here we specifically talked about the Hess's law of constant heat summation, and also we saw that how in case of bond enthalpy of atomization can be addressed. And also we went through a problem which was a numerical problem that was based on the concept of standard enthalpy of combustion. So in today's class, we will specifically talk about the homolytic bond dissociation energy. So in this case, the bond dissociation enthalpy plays a pivotal role, and what we actually mean by bond dissociation energy. So as you can see over here, let me just bring out a pen. Yeah. So the homolytic bond dissociation energy is the amount of energy required to break apart, or actually to one mole covalently bonded gases into a pair of radicals. The SI units that are used to describe the bond use energy are kilojoule per mole of the bond. Now, it actually indicates how strongly or how weakly the atoms are bonded to each other. So the SI unit that are actually bonded here. So we are going to the introductory part, which is breaking a covalent bond between two partners that are A and B. So we have a covalent bond between two partners A, B. You see over here, there is a covalent bond between A and B. And we are actually discussing here about the delta BD of H in standard state. So it is actually delta BD. This BD stands for bond dissociation, and H is actually enthalpy. So that is delta of bond dissociation H minus. So breaking a covalent bond between two partners A and B either can occur by the homolytic bond cleavage or by heterolytic bond cleavage. So if we take up the situation where the heterolytic bond cleavage occurs, heterolytic bond cleavage means the after the bond cleavage, the two partners will be different from one another in charge. So it will be heterolytic bond cleavage. If the bonded electrons are taken up by B, it will be A plus B minus. So A cation and B anion. Or else in this case, if the bonded bond pair is taken up by A, it will be A minus B plus. So A will be anion and B will be cation. So these are the heterolytic bond cleavage scenarios. If we take up the homolytic bond cleavage scenario, then there will be one electron that will be shared by each of the partners. So here we have A and B. If one electron from the bond pair is taken by A and another electron is taken by B, then it will be two radicals, A dot and B dot. That means A radical and B radical. This dot actually refers to a radical species. As actually it is shown here, the product of homolytic bond cleavage are radicals, and the energy that is needed to break the bond homolytically, that is called the bond dissociation energy. That is the BDE. In short, it is termed as BDE, which is the bond dissociation energy. Now, BDE is a measure of the strength of the bond. So I guess you guys have got an idea about the bond dissociation energy. So here we are talking about BDE. So we have actually a covalent bond. We have a covalent bond, and then we are trying to keep the covalent bond between two radicals, and that is called the homolytic bond cleavage. And in case of homolytic bond cleavage, it is measured as the BDE, that is the bond dissociation energy. Now, BDE for a molecule, when it is termed as AB, is calculated as the difference in the enthalpy of the formation of the products and the reactants for homolysis. So, when what is the BDE? If we take up the equation 3, you can see the products are A dot and B dot, and the reactant is AB. So the BDE for this reaction will be delta H formation. This F actually stands for formation. This delta F H of A dot plus delta F H of the B dot minus delta F H of AB. So it will be the difference in the enthalpies of formation of the products and the reactants in homolysis. Now, officially, the IUPAC definition of the bond dissociation energy refers to the energy change that occurs at 0 Kelvin, and the symbol for it is D0. However, it is commonly referred to as BDE, that is the bond dissociation energy. So, whenever the energy change is occurring at a 0 Kelvin, that is the absolute temperature, then it is actually used imprecisely or interchangeably with the bond dissociation energy, that is BDE or D0. Now, actually, actually the bond dissociation energy, which refers to the enthalpy change at the room temperature. Although there are technically differences between BDEs at 0 Kelvin and 298 Kelvin, but these differences are not very large and generally do not affect the interpretations of chemical processes. So here you can ask me that, sir, you said that energy change is occurring at 0 Kelvin, that is termed as D0. So D0 is actually the bond dissociation energy at 0 Kelvin. And we are taking up the BDE value at 298 Kelvin. That is room temperature 25 degrees Celsius. Now I am seeing these two terms are actually similar and used simultaneously or albeit imprecisely and interchangeably. So I can write BDE instead of D0. But then you will ask that one is at 0 Kelvin, sir, and another is at 298 Kelvin. So why can we use two different parameters? Because they are taken up at two different temperature values. Why is it so? Because the differences between 0 Kelvin and 298 Kelvin bond dissociation energies are not that much large. And generally, the interpretation of the chemical process do not get hampered if we take the assumption from 0 Kelvin to 298 Kelvin. And so that's why what happens in this case, we can interchangeably use bond dissociation energy with Day0. So this is the general equation for our enthalpies of formation. That is the BDE for the molecule. So enthalpies of formation is BDE. As you can see over here, the equation that is here, the BDE is delta FH of A dot, that is one of the products, plus delta FH B dot, that is one of the products, minus delta FH of AB, that is the reactant. So that is the IUPAC definition of bond dissociation energy, that is BDE. A molecule AB is called the enthalpy of formation. Now we will move on to the next case where we will discuss about the bond breaking or bond making procedure. So how we can actually take up this as a very good or classical example. So bond dissociation energy, as I have told, that it is very much trivial because in most of the cases, the bond dissociation energy will be between a homolytic bond. Now let's take up this reaction whenever we are calling it as a bond dissociation energy, that is a enthalpy. So BDE is actually an enthalpy parameter and it is a state function. And since it is state function, so as you know, a state function's value does not depend on the path that it chooses. The specific mechanism that how the bond is actually breaking or how the bond is getting formed does not affect the BDE value because enthalpy is a state function and it does not depend on the path that is chosen. And that's why the delta BDH minus value does not depend upon the path. These are very useful in assessing the energetics of chemical processes. Now, for chemical reactions, if we combine the bond dissociation energies or for bonds formed and bonds broken, then we can easily apply Hess's law over here. In the last class, I have specifically discussed about Hess's law of constant heat summation, and it can be used to estimate the reaction enthalpies. So let us take an example of chlorination of methane. So this is methane CH4 and we are chlorinating it with the help of Cl2. And the product is one is methyl chloride, that is CH3Cl plus HCl, that is hydrogen chloride gas. So now the overall reaction thermochemistry, it can be calculated exactly by combining all the BDEs for the bonds broken and the bonds formed. So we will first see how it happens. From CH4, we have got two products. One is the CH3 dot, another is the H dot. So that is actually BDE of the CH3H bond. So we have CH3 and we have a bonded of H. So this is the bond we have in methane, that is in CH4. And in methane, if we cleave the bond just like this by single electron transfer on both the atoms, on carbon, on a hydrogen. So we will have the methyl radical and we have the H dot radical. So we have these two radicals. Also, we have a reagent Cl2. So Cl2 bond breaking will be Cl2 to 2Cl dot. So that we will consider the BDE of the Cl2. So we have a Cl and we have another Cl. One electron on this Cl, another on the another Cl. So it will be two Cl dots will be formed. For the first case, one methyl dot and one H dot is formed. Now we have H dot here, we have a Cl dot here. So now we are forming HCl. This H dot and methyl dot. These were two products. And from this we had two Cl dot. And these two actually combines to produce HCl. Now, as you can see, I have written over here minus of BDE of HCl. Why does the minus comes? Because the minus is coming because in case of a bond dissociation energy or BDE, when the bond dissociates, we term as BDE. When there is a bond formation, that is H dot and Cl dot is accumulating or aggregating to produce HCl, it is rather bond making. So this is a bond making energy. So bond dissociation energy and bond making energies are exactly same in magnitude, but just the opposite in sign. And that's why it is minus of BDE of HCl. And next we have this CH3 dot and Cl dot, and they actually get combined and we form the CH3Cl. And that's why it is minus BDE of CH3Cl. So entirely we have the equation CH4 plus Cl2 producing CH3Cl and HCl. Because you see this CH3 dot in this side and this CH3 dot on the right hand side gets cancelled. Also, these two Cl dot and these two Cl dot are cancelled. And we are having this H dot and this H dot is cancelled. So we are ultimately getting CH4 plus Cl2 to HCl plus CH3Cl. Now delta H for the reaction is BDE of RH plus BDE of Cl2 plus minus BDE of HCl and plus minus BDE of CH3Cl. So ultimately, we are having this equation. We are adding all these equations all together, and we are having the delta H value of all these BDE of CH3H plus BDE of Cl2 plus BDE of HCl plus minus of BDE of HCl plus minus of BDE of CH3Cl. So that's why the reaction enthalpy is a state function, so it does not matter what reactions are combined to make up the overall process. So using Hess's law. However, BDs are convenient to use because they are very readily available. Now, alternatively, these BDs can be used to assess individual steps of a mechanism too. So, for example, if we take up a very interesting step of free radical chlorination of alkene, alkene means RH. This RH is actually an alkene. And we are performing free radical chlorination of alkenes is the abstraction of hydrogen atom from the alkene to form a free radical. So we have RH, we have Cl dot. Now from this RH, this H dot will be abstracted by Cl dot to produce HCl, and R dot, a free radical, is actually produced. The energy change for this step is equal to the difference in the BDs of RH and HCl. So we have delta H is equal to BDE of RH minus BDE of HCl. This relationship shows that the hydrogen abstraction step is the more favorable step when BDE of RH is smaller. The difference in energies accounts for the selectivity of the halogenation reaction of hydrocarbon with the different kinds of CH bonds. Now, there is a scientist, Gronat, who has proposed that the variation in BDE is also explained by resulting from the destabilization of the reactants because there are steric repulsion between the substituents, which is released in nearly planar radicals. Nearly planar radicals means what? So we have radicals. If you see classically, if we take up the methyl radical, so we have a carbon atom. We have three hydrogen atoms, and we have a radical over here. Radicals means there is a single electron. So this is the structure of the methyl radical. In this case, the destabilization of reactants is due to the steric repulsion of the substituents. You see in this methyl radical case, their substituents are very small hydrogen atoms, which are very small in size, and that's why there is no steric repulsion between the hydrogen atoms. Considering that BDs reflect the relative energy of the reactant and the product, this explanation can account for the trend in BDs. And another factor that is very important in case of BDE determination is the electronegativity parameter. So this is the electronegativity parameter that is very much important. And as you know, there are different scales for calculating the electronegativity of atoms. I guess you have read a lot about electronegativity in the chapter of periodic table. And there the electronegativity is defined by many scales. There are Mulliken scale, there are Pauling scale, there are Adelaide-Rosser scale. And in this case, we will talk about the Pauling definition of electronegativity because it is one of the most widely regarded scale of electronegativity consideration. And it says that the bond resolution energy that is between two unequal partners. Unequal partner means the two atoms are different from one another. So that will be dependent upon the difference in electronegativity. So suppose we have the molecule where it is AB. AB is a molecule where A and B are different atoms. Now we have got the D0 of AB. So we have to calculate the bond dissociation energy, that is a BDE of AB. It will be D0 of AA bond plus D0 of BB bond divided by 2 plus chi A minus chi B whole square. So let us take up the value, that is the value of chi A and chi B. So how we will practically apply this in case of any molecule that we consider. So therefore this we have to see what is the electronegativity of the atoms. So let us we take the example of HF molecule, that is hydrogen fluoride. HF is a very non-stable molecule and it falls under the category of AB because these two atoms are chemically different from one another. These two atoms are hetero. So if we calculate the D0 value of HF, so then according to this equation, it will be half of the addition of the D0 value of AA and BB. So A here stands for H. So D0 of HH plus D0 of FF plus it will be chi A minus chi B whole square. So it will be chi of H minus chi of F, its whole square. Now this chi actually is the Pauling scale electronegativity of a specific atom. So as we know, chi of H is 2.2 in Pauling scale. And in the periodic table chapter, you have know that fluorine is the most electronegative substituent atom in the periodic table, which has a chi value of 4.0. So if we put up the value of D0 of the HH, that is the bond dissociation energy of dihydrogen molecule plus the bond dissociation energy of the fluorine molecule. And then if we add all these terms and put the values over here, we will ultimately be able to calculate the D0 of HF. So whenever you are given two heteroatoms and when you will have these values, that the HH value dissociation and the BB value of the dissociation. And then you remember the fact that the electronegatives are given to you, or if they are very known atoms, you have to remember the electronegativities also. So I will suggest you to please go through the periodic table chapter and to remember what are the electronegativity parameters of the different atoms. So then if we put the values over here, we will definitely get the ultimate D0 of the AB in the kilojoule per mole energy. So thus we can calculate the bond dissociation enthalpy of a specific molecule, which is preferably diatomic in nature, because this is actually holding for a diatomic molecule. Now we will come to a more detailed discussion about the bond enthalpy. Now, chemical reactions that actually involve the breaking and making of the bonds, in this case, energy is actually required. Energy is required in every case. Now, it is possible to relate that heat of the reaction of this energy is associated with the reference to the enthalpy changes in the chemical bond formation. Now, two different terms are actually used in thermodynamics. The first one I have already talking about, the bond dissociation enthalpy, BDE. And second one is the mean bond enthalpy, MBE. So till now, I have actually discussed about the first one, that is the bond reducing energy. But these terms will be referred to with reference of the diatomic and polyatomic molecules also. Because till now, I have already discussed about the diatomic molecules, but I have not taken up any reference for the polyatomic molecules. So polyatomic molecules mean there will be more than two atoms. That's why it is termed as poly. Now, if we take up the very classical reaction, that is the in case of dihydrogen to H atom. So from H2 gas, they will be producing two hydrogen atoms. And the delta H of H minus is 435 kilojoule per mole. This BD stands for the bond dissociation of this HH bond. So we have got the equation, that is thermochemical equation, because the reaction is H2 gas to 2H, which is balanced, and we have got the delta BDH minus as 435 kilojoule per mole. So this enthalpy change involved in this process is the bond dissociation enthalpy of the HH bond. The bond dissociation enthalpy is the change in enthalpy when one mole of the covalent bonds of a gaseous covalent compound is broken into final products in the gas phase. So it is the same enthalpy for the atomization too. In the last class, I have told you in case of diatomic molecules, the atomization enthalpy and the bond dissociation enthalpies are same. They can be used interchangeably. So also in case of Cl2 and in case of O2 also, we can define these parameters. Whenever the from Cl2 to 2Cl, there will be bond dissociation enthalpy. It is around 242 kilojoules per mole. And in case of O2, if we produce two oxygen atoms, the BD is 428 kilojoules per mole. So as these cases, all the cases, the delta BDH minus is actually equal to delta AH minus. That is the atomization enthalpy. But in case of the polyatomic molecules, the bond usage enthalpy is different for different bonds within the same molecule. So now consider a polyatomic molecule, that is methane. Methane is a polyatomic molecule because methane has 5 atoms. So we have 5 molecules over here. So we'll consider 5 atoms. That's why methane is a polyatomic molecule. The overall thermochemical equation, if we atomize methane, will be CH4 in gas. It will produce 1 carbon in gas phase plus 4 hydrogen in gas phase. The delta atomization of H value in this case is 1665 kilojoule per mole, which is quite high because in this case, four CH bonds have to be broken. So in these four CH bonds, they are all identical, and they are all identical not only in terms of bond length but in terms of bond energy too. But the energies that are required to break the individual CH bonds in each successive step, they actually differ. So you can say that, sir, you're saying all these CH bonds are equal. These CH bonds are equal. All these CH4 bonds are equal in bond length. There are four CH bonds. But as we go from CH4 gaseous to CH3 gaseous plus H gas, then from CH3 gaseous, if it goes to CH2 gaseous plus H gas, and likewise, if you study step by step, you will see in all the cases, the successive cases, the individual CH bond production energy will differ. So from CH3 to C gas plus 4H gas, if we go via CH3 plus H, then from CH3 we get CH2 and H. Then from CH2 we are getting CH plus H, and ultimately we will get CH2, CH3 plus H. So from CH4, we are having CH3 plus H. From CH3, we have CH2 plus H. From CH2, we'll have a CH plus H. And in the last step, we have C plus H from CH. So we have got four equations over here. From CH4 to CH3H, CH3 to CH2 H, CH2 to CHH, and from CH will be C and H. Now, all the CH bonds are identical, and but still, in all the steps, the bondation energy, that is delta bond of H, is different. In this case, the delta H value is 427. In this step, the delta H value is 439. Next step, the delta H value is 452. And in the last step, it is 347. So if we add up all these equations, you will see this CH3 and this CH3 gets cancelled out. This CH2 and this CH2 cancelled out. This CH and H get cancelled out. So we have got four hydrogen, one carbon on the right hand side, and one methane on the left hand side. So ultimately, we go back to the parent equation. And if we add all these, we will have these four items will actually lead to 1665 kilojoule per mole. So in these cases, we will see all the cases are actually different. And that's why in this case, we will have the mean bond enthalpy in action. So we will take a mean of all the bond excitation energies. So for this example, we will have the delta CH of H minus value will be 1/4 of 1665 kilojoule per mole. So it will be around 416 kilojoule per mole, which is the mean bond dissociation enthalpy, mean bond enthalpy. So when there is a polyatomic molecule and we have multiple bonds, then we will not take the PDE value, but instead we will take the MBE value. So we find here that the mean reduction enthalpy, that is a CH bond enthalpy in this case, is 416 kilojoule per mole. It has been found that the mean CH bond enthalpy differ slightly from compound to compound. So as you can say that, sir, what will happen for the mean reduction enthalpy in case of CH3 CH2Cl, that is ethyl chloride? Or if we take up the example of CH3CN, so in this case, etc. But others not differ in a great deal. So you can say this molecule also have CH bonds. And in case of methane, the CH bond energy was 416 kilojoule per mole. But what happens when we will take up different compounds like ethyl chloride or like acetonitrile or like methanol? So in these cases, I can say the value may have differed a little bit, but it will not be such great that our interpretation will be long. Now, this using the Hess's law, we can actually calculate the bond enthalpy. The bond enthalpy values of some single and multiple bonds will actually be given, and reaction enthalpies are very much important in this case. The reaction enthalpy. So we will take up the reaction enthalpy, the del R H value. So del R, in case of the del R H value, how it can be calculated. So if we take up the equation del R H, what will be the del R H value? So if we have to calculate the different bond enthalpies of the del R H value, we will have the summation of the bond enthalpy of the reactant minus summation of the bond enthalpy of products. So in this way, we can calculate the reaction enthalpy. The reaction enthalpies are very important quantity because they arise from the change that accompanies the breaking of the old bond and making of the new bonds. And so we can predict enthalpy of a reaction in a gas phase. This relationship is very much particularly more useful when the required values of the del RH are not available. The net enthalpy change of a reaction is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy that is required to break all the bonds in the product molecules. And this relationship is approximate and is valid when all the substances, that is the reactants and products, are in their gaseous state. So I would say that this equation is an approximate equation, not an exact equation. So this is an approximate equation, and when all the reactants and products are in gas phase, you have to remember the fact that all the reactants and products have to be present in the gaseous phase. And then only this equation can be valid. Now there will be some mean single bond energies that will be given here. We have the high for hydrogen, it is very much high, that is 436. In case of oxygen, the value is quite high, that is 464. All I am talking about the mean bond enthalpy, mean single bond enthalpy. In case of oxygen, the value is 464. In case of hydrogen, the value is 436. In case of fluorine, the value is quite high, 569. Likewise, we can tell what are the mean value of the enthalpies. So for fluorine with hydrogen, this value is actually very much high, the mean value enthalpy. These are all with respect to hydrogen. This 436 value is with also hydrogen. So it is a homoatomic nature. And this case, it is also with hydrogen, the OH bond. And also you can see if we go from fluorine to fluorine, the value becomes very much less. You can say why in case HF, the value is quite high, but why in case of FF, the value is very much low. The value in case of FF is 155. So there is a striking anomalous nature between these two. As you can say, the HF value's mean bond enthalpy is very much high rather than the FF value of 155. Why is it so? This can be actually discussed in case of the at a periodic table, but here since the topic has come up, I will give you a bit of hint. You see, fluorine is a very strong electronegative element and which is small in size. So we have an F bond. We have to explain the fact that why in case of FF bond, the mean value enthalpy is so much low. Low means there is very much less energy is required to break this bond. As you know, the halogens electronic configurations are NS2, NP5. So with the one odd electron, this bond will be formed and there will be 3 lone pairs on each fluorine atoms. And you have talked about these as lone pairs of electrons. And when lone pairs of electrons are there are very high electronic repulsion between the lone pairs because the inter-electronic repulsion operates. And here you can see that there are 3 into 3, that is 6 lone pairs, which is even a very close proximity because fluorine atom is very much small in nature. And that's why the FF bond length is very much low. And as you know, if the bond length is low, the bond using energy could be high. But in this case, because these lone pairs experience very high steric repulsion, that's why despite the bond length is very much short, the bond length energy will be very much low because these lone pairs will actually perform inter-electronic repulsions and will make this bond weaker. That's why this bond gets cleaved very much easily. And that's why this FF bond is energy is very much low. That is the reason. Now we will move our discussion to the next case where we will talk about the enthalpy of solution. So what do you mean by enthalpy of solution? So when a substance is actually dissolved, when one mole of substance is actually getting dissolved and 1 per mole we will calculate and then the change in enthalpy is actually termed as the enthalpy of solution in a specific amount of solvent. So whether enthalpy change when a 1 mole of substance is solvated in a specific amount of solvent, then the enthalpy change is observed is the delta H solution. The enthalpy of solution at the infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent when the interactions between the ions will be negligible. That is the solute molecules. That is called the infinite enthalpy of solution at infinite dilution. Now, when we are taking up an ionic compound, let's say we are talking about an ionic compound which is termed as AB. It is solid in nature. And if it is performing this solution and the energy generated is delta H solution, we will find A plus aqueous. So the solvent is taken up as water because water is one of the most universally accepted solvents, plus B minus aqueous. So we have got the equation. AB is a solid which is dissolved in a suitable solvent, and we are getting A cation and B minus anion. Now, how we can actually break the equation over here? This ionic compound, when dissolves in the solvent, the ions actually leave their ordered position in the crystal lattice. If the AB solid is there, there is a lattice. A lattice means, suppose this is a cubic lattice, where there will be A, B, etc., and all these things will be present. The cubic lattice. And let's say here A and B's are present. So if we have to solvate A and B in the water, then I have to actually have the ions leave their ordered position. These A and B ions will come out from their ordered position in the crystal lattice. So the lattice should be broken for the AB to be solvated. And there are now more free in the solution, but solvation of these ions, that is the hydration in case of solvent in water, also occurs at the same time. So if we have to complete diagram from AB solid, we have to produce some lattice enthalpy, that is the delta lattice H, minus. Minus means it is in the standard state. So we from AB we are producing two things: A plus gaseous, so A plus cation, that will be gaseous state, and B minus anion, also it will be in the gaseous state. And now we have also A plus gaseous and B plus gaseous, which are more free in solution. Now I will give them the delta hydration of H, that is the hydration energy, and then now they will be solvated in water molecule. So now we have this diagrammatically for an ionic compound, the enthalpy of solution of AB, that is delta solution of H in water, therefore determined by the electric values of the lattice enthalpy with the delta hydration of H. So this delta solution of H is actually, so by this path or by this path, if we go, since enthalpy change is a state function, it does not depend on the path that we are choosing. So delta solution of H is equal to delta lattice of H plus delta hydration of H. So ultimately, since enthalpy value is a state function, so in this case, what we will have? Delta solution of H will be equal to delta lattice of H plus delta hydration of H. And since enthalpy is a state function, so its value does not depend on the path. For most of the ionic compounds that we will deal, that will see delta solution of H is actually greater than 0. That is positive. So we have to give actually energy to the solid to make it soluble. That's why the dissociation process is actually endothermic in nature. So that's why in most of the cases, the delta solution of H is endothermic because it is positive in most of the cases. So that's why the solubility of most salts in water increases with the rise of temperature. If the lattice enthalpy is very, very high, the dissolution of the compound may not even actually occur. So why do many fluorides tend to be less soluble than their corresponding chloride? So we have a MF salt, metal fluoride salt, and we have a MCl salt, that is the metal chloride salt. You see, the MCl salt will be readily soluble in water, but the MF salt will have low solubility. Estimates of the magnitudes of the enthalpy changes may be made by using the table. That's why if the lattice enthalpy is very much high, if the lattice enthalpy is very much high in value, if it goes beyond the value, then the delta hydration of H will not be enough to make the value very much less. And so the delta hydration H value is actually negative. So that actually helps in making the delta solution of H value lower. And so in case of the fluoride ions, since metals forms very strong bond with the fluoride ions, that's why the MF actually do not perform to have a very high delta lattice of energy value. So there is lattice enthalpy. The lattice enthalpy, that is delta lattice H, that we are considering over here, the lattice energy, it is actually the of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in the gaseous state. So if we take up the example of NaCl, which is very much common in our household, that is the table salt. If we have the NaCl solid and if we have to take up the lattice enthalpy, so we need to actually break this NaCl into a corresponding cation and anion, and that too in the gaseous phase. So we will break the NaCl between Na plus and Cl minus in the gaseous state. And if we see the delta lattice H value of NaCl in the standard state, that is minus, it will be 788 kilojoule per mole. So very much high energy is required to actually break the bond between NaCl and make them in their gaseous state. Since it is impossible to determine lattice enthalpies directly by experiment, because if we have to perform it experimentally, we will have to heat up the corresponding compounds or substances, and we'll have to see when they are made into a gaseous form. So that is actually quite impossible to perform on an experimental platform. That's why an indirect method will be applied in case of this. That's why the term of Born-Haber cycle comes into picture. So that's why we need to have the Born-Haber cycle. So with this, today we conclude our talk, because in the next class we will start talking about the Born-Haber cycles. So in this class, what did we learn? We learned about all these enthalpy parameters, the bond dissociation enthalpy parameters, and also we saw how from the solution state we can determine the delta solution of H. And also we had a brief idea about the Born-Haber cycle, which tells us that whenever a solid is actually made into its constituent cations and anions in the gaseous form. In the coming lecture, we will see how a Born-Haber cycle is prepared and how we can determine the corresponding delta solution H value from the Born-Haber cycle. So if you have any question or any doubt regarding any of the slides, you can go ahead and ask.